There is a specific kind of discomfort that does not appear in press releases. It does not make headlines the way a rocket launch does, or a photograph of a distant planet. It lives in the language of academic papers, in phrases like in tension with current models, and requires further investigation and cannot be accounted for within the standard framework. It is the discomfort of scientists who have spent careers building the most precise map of the universe ever constructed, and who are now finding that the territory does not match the map. Not in one place, not in one field, in 5. Simultaneously, using instruments that have been checked and rechecked and checked again. Tonight, we're going to sit with that discomfort together. We are going to look at what deep space is returning. The actual data, the actual numbers, the names of the researchers holding it. We are going to understand why some of the most careful minds in science are describing this moment quietly and precisely as one of the most unsettling in the history of cosmology. This is not alarm. This is not sensationalism. This is what it looks like when the universe refuses to fit the model we built for it. If you find yourself returning to these questions, the ones that stay open after the lights go out, consider subscribing. Every script on this channel is built for the listener who wants the real depth, not the summary. There is a specific kind of discomfort that scientists do not talk about in press releases. Science has a public face that is confident by design. Discoveries are announced. Milestones are celebrated. The language of institutional science is the language of progress, of problems identified, experiments run, conclusions drawn. This is not dishonesty. It is the way science communicates to a public that needs to understand what its investments have produced. But inside the field, there is a different kind of conversation. It happens at conferences in the questions that follow a presentation. It happens in the acknowledgement sections of papers, where researchers thank colleagues for illuminating discussions about results that do not fit. It happens in the measured, careful language of a review article, where a senior researcher writes that a particular measurement remains in tension with the standard model. Every reader in the field understands that this phrase, in this context, carries a weight that the words themselves do not fully convey. What that language describes is the experience of holding data that you cannot explain, not data that is noisy or ambiguous or preliminary. Data that has been checked. Data that has been published, peer-reviewed, replicated with independent instruments, and rechecked again. Data that should fit the model, and does not. This is what scientific worry looks like. It is not panic. It is not crisis in the tabloid sense. It is the precise, specific discomfort of a measurement that will not resolve. And it is worth understanding what that discomfort actually means, because the language scientists use to describe it is so careful, so deliberately underplayed, that its true significance is easy to miss. In any measurement, there is noise. Random variation, instrument quirks, statistical fluctuation. These produce results that deviate from expectation by small amounts. Scientists quantify this deviation in units called sigma. 1 sigma means the result is one standard deviation from what the model predicts, the kind of variation that could plausibly appear by chance. 2 sigma is more unusual. 3 sigma begins to attract attention. At 5 sigma, the probability that the deviation is a statistical fluke drops to 1 in 3.5 million. In particle physics, 5 sigma is the formal threshold for declaring a discovery. It is the number that separates interesting anomalies from things that demand explanation. The most prominent of the anomalies we will be discussing tonight sits at 5 sigma and has been there for years. It has not shrunk with better data. It has grown. the researchers expressing concern about what deep space is returning are not at the fringes of their fields. Adam Ries, who shared the Nobel Prize in Physics in 2011 for co-discovering the accelerating expansion of the universe, has described one of these measurements as indicating that something is fishy in our current understanding, language that. From a Nobel laureate publishing in peer-reviewed journals is the equivalent of a fire alarm. Wendy Friedman, one of the world's leading experts in measuring cosmic distances, has watched a measurement she spent decades refining produce a result that creates more complexity rather than less. George Efstathiou at Cambridge, one of the architects of the standard model of cosmology itself, has stated publicly that the primary anomaly is not going away and may require what physicists call new physics, a term that means precisely that the current framework is insufficient. These are not people given to overstatement. The culture of physics actively selects against it. When researchers at this level, in these terms, describe their discomfort with what the instruments are returning, the appropriate response is to listen carefully. What the instruments are returning is this: across 5 independent fields of astronomy and physics, using 5 different sets of instruments operated by 5 different research teams working with 5 different physical phenomena, the universe is producing measurements that disagree with the best model ever constructed to describe it. The disagreements are not going away. Several of them have grown stronger as the instruments improved. The instruments are working correctly. The mathematics has been checked. The worry is in what the results say. It is worth being precise about what this means for the listener. The anomalies we will be examining are not borderline cases. They are not findings that a single research team produced in isolation and that the broader community regards with skepticism. They have been independently confirmed, in some cases by multiple separate groups using different methods, and they have been the subject of formal review in the most prestigious journals and conferences in the field. The Astrophysical Journal, Nature, Science, Physical Review Letters. The papers describing these anomalies are not preprints sitting on servers waiting for peer review. They are the published record of what the field's best instruments have returned, assessed by the field's most rigorous processes. What makes this moment unusual is not the existence of anomalies. Anomalies exist in science at all times. What makes it unusual is the combination of 3 properties that these particular anomalies share. They are statistically significant enough to demand attention rather than patience. They have survived the scrutiny that should resolve them if they are errors, and they appear across multiple independent fields simultaneously. The combination of these 3 properties is what distinguishes the current situation from the ordinary experience of science encountering unexplained phenomena. Individual anomalies are routine. Correlated anomalies across 5 independent fields, all surviving systematic review, are not. To understand why what we are finding matters, you have to understand what we thought we had. For roughly 30 years, cosmology operated with a level of confidence that is rare in science. The model built during that period, known as lambda CDM for the cosmological constant lambda and cold dark matter, is the most successful predictive framework in the history of the field. It is what physicists mean when they say the standard model of cosmology, using the same kind of language particle physicists use when they refer to their own standard model of particles and forces. The comparison is intentional. Lambda CDM held that status because it earned it. Lambda is the symbol Einstein introduced for the cosmological constant, a term representing the energy of empty space itself, now understood as dark energy, the force driving the accelerating expansion of the universe. CDM stands for cold dark matter, matter that does not interact with light, cannot be directly detected, but whose gravitational effects on visible matter are measurable and real. Together, these two components, alongside ordinary matter and radiation, make up the full content of the universe under the model. Current estimates, built from multiple lines of evidence, suggest roughly 68% dark energy, roughly 27% dark matter, and roughly 5% ordinary matter, the atoms, molecules, and everything built from them that make up everything we have ever directly touched or seen. This composition was not invented to fit a single dataset. It was derived from 4 completely independent lines of evidence that all converged on the same answer. The first line came from the cosmic microwave background, the faint afterglow of the Big Bang itself, a bath of microwave radiation that fills the entire sky at a temperature of 2.725 Kelvin. The CMB encodes the initial conditions of the universe and its temperature fluctuations, and lambda CDM predicted the precise pattern of those fluctuations before they were measured with high resolution. When the measurements came in, they matched. The second line came from the large-scale structure of the universe, the way galaxies cluster into filaments, walls and voids across billions of light years. Lambda CDM predicted the statistical properties of this structure. The surveys confirmed them. The third line came from the measurement of Type 1a supernovae, exploding white dwarf stars used as standardizable distance markers across cosmic scales. The supernova surveys of the 1990s, including the work that would earn Adam Ries his Nobel Prize, confirmed that the expansion of the universe is accelerating, a prediction lambda CDM accommodates through dark energy. The fourth line came from Big Bang nucleosynthesis, the process by which the light elements hydrogen, helium, and lithium were forged in the first few minutes after the Big Bang. The predicted ratios of these elements matched what we observe in the oldest stars. 4 independent measurements. 4 separate physical processes. 4 different instruments and techniques developed over decades by different research groups, all 4 pointing to the same picture of the universe. This is what scientific confidence looks like when it is genuinely earned. It is not one team saying one thing. It is every team, using every available tool, arriving at the same answer from different directions. By the time the European Space Agency's Planck satellite completed its primary mission in 2013, mapping the cosmic microwave background across the entire sky at a resolution of 0.01 degrees, lambda CDM had been stress-tested more thoroughly than any cosmological model in history. It had passed every test. The James Webb Space Telescope launched on December 25, 2021. Its primary mirror spans 6.5 meters, 4 times the light-collecting area of Hubble. It operates in the infrared, wavelengths that allow it to see through dust and to observe light that has been stretched by the expansion of the universe over billions of years. Light from objects so distant and so old that they existed when the universe was only a fraction of its current age. JWST was designed to push the redshift frontier, to look further back in time than any previous instrument and see the first galaxies as they assembled from the primordial gas. The scientific community was not anticipating surprises. The mission was designed to provide confirmation at unprecedented resolution, to see the early universe with enough clarity to test lambda CDM predictions in detail, not to overturn them. When the first full-colour images were released on July 12, 2022, the response was the kind of celebration that comes from arriving somewhere you have been trying to reach for decades. The images were, by any measure, astonishing in their detail and depth. There is something worth sitting with here before we proceed to what happened next. The lambda CDM model was not built to be defended. It was built to be tested, and for 3 decades, every test confirmed it. This is the nature of good science. a model that survives falsification attempts becomes more credible with each attempt it survives, not because scientists become emotionally attached to it, but because the probability of a model that is fundamentally wrong surviving every test decreases with each test passed. By the time JWEST launched, Lambda CDM had passed dozens of independent tests using different phenomena and different instruments. Its parameters were known to single-digit percentage uncertainties. It was the most precisely validated cosmological model ever constructed. This context matters for understanding the significance of what followed. The researchers who built JWEST, who calibrated its instruments, who designed the observing programs that would use its first year of operations, these were not people hoping to find something wrong with the standard model. They were people who had built the most powerful astronomical instrument in history to see the universe more clearly than it had ever been seen. What they expected was confirmation, a crisper view of a universe they already understood. What JWEST was going to show us, everyone agreed, was the same universe, only crisper. Within months of first light, something was wrong. Lambda CDM makes a specific prediction about what the very early universe should look like. In the first few 100 million years after the Big Bang, the universe should be filled with a raw material of galaxy formation, clumps of gas and dark matter beginning to collapse under gravity, seeded by the small density fluctuations imprinted in the CMB. The first structures to form should be small and irregular. Galaxy formation takes time. Gas must cool. It must collapse. Stars must form, burn through their fuel, explode as supernovae, and seed the next generation of star formation with heavier elements. The process is not fast. It is cumulative, generational, built on its own previous outputs. At the highest redshifts JWEST could reach, the most distant objects it could observe, corresponding to the earliest periods of cosmic time, the model predicted that we would find proto-galaxies, small, clumpy, irregular structures in the early stages of assembly. Not mature galaxies, not large, settled, well-organized systems with billions of stars already formed. The architecture of a fully realized galaxy takes hundreds of millions to billions of years to construct. What JWEST found was different. In February 2023, a team led by Evo Lab at Swinburne University of Technology published a paper in the journal Nature. The paper reported the detection of 6 candidate galaxies at redshifts between 7.4 and 9.1, corresponding to a period when the universe was between roughly 550 million and 700 million years old. This is not unusual by itself. JWEST was built to see galaxies at these redshifts. What was unusual was the estimated stellar masses of these galaxies. The team's analysis suggested that these 6 objects contained stellar masses comparable to, and in some cases exceeding, the most massive galaxies in the universe today. They were not proto-galactic clumps. They were apparently massive, structured systems, the kind of galaxies that should, by every model of galaxy formation, have taken billions of years to build. The universe was roughly 550 to 700 million years old when these galaxies existed. To put that in proportion, the entire span of complex life on Earth, from the first multicellular organisms to the present, is approximately 600 million years. These galaxies had formed, built up their stellar populations, and settled into organized structures in a window of time smaller than the one it took life on this planet to go from the first animals to the present moment. Under every model of galaxy formation that existed when JWEST launched, that timeline was not possible. The science team's first assumption was calibration. Early JWEST observations used photometric redshifts, estimates of distance based on how the light from an object appears across different wavelengths, which shifts predictably with distance. Photometric redshifts have known uncertainties. The initial hope was that spectroscopic follow-up, direct measurement of specific spectral lines in the light, which gives a precise and unambiguous distance, would bring the masses down, place the galaxies at lower redshifts, and return the picture to something the model could accommodate. Spectroscopic confirmation, when it came, did not bring the masses down. For several of the candidates, it confirmed both the distances and the masses as genuine. The galaxies were where the photometry placed them. They were as massive as the initial analysis suggested. JWST has a resolving power sufficient to distinguish a penny at a distance of 25 miles. It is the most precise astronomical instrument humanity has ever pointed at the sky. The same instrument that generated these anomalous results is the instrument that makes the results hardest to dismiss. When your most precise tool returns a measurement that contradicts the model, you do not blame the tool. You sit with the measurement. 6 galaxies where the model said there should be none. The catalogue of anomalous early galaxy candidates has grown since the lab et al. Paper, JWST's observing program has continued to produce redshift confirmations across multiple galaxy survey fields, and the number of spectroscopically confirmed massive early galaxy candidates has expanded beyond the original 6. The picture has not simplified with more data. It has become more clearly anomalous. Some of the candidates confirmed at the highest redshifts are not just massive, they show evidence of having already formed and then quenched their star formation, meaning not only did they assemble billions of solar masses in a few 100 million years, they also ran out of fuel and stopped forming stars during a period when, by the model, they should still have been in the early stages of assembly. A galaxy that has already quenched its star formation by the time the universe is 700 million years old presents a problem that is qualitatively different from a galaxy that is merely massive. It requires not just fast formation, but fast formation, peak activity and shutdown, the full galaxy life cycle compressed into a period that should not have been long enough for any of those stages to complete. The current state of the JWST early galaxy literature is one in which each new confirmed observation narrows the range of possible explanations rather than opening new ones. The question that immediately follows is whether the model can be adjusted to account for these galaxies without breaking everything else. This is the standard approach in science when data deviates from prediction. You look at the model's parameters, the inputs and assumptions that drive its outputs, and you ask whether changing them within their allowed ranges can bring the prediction into agreement with the observation. This is not special pleading, it is legitimate scientific practice. Models are approximations. Their parameters carry uncertainties. Finding the parameter range that best fits all available data is what scientists do. For the JWST early galaxy problem, the adjustments that have been tried include increasing the assumed efficiency of star formation in the early universe, making the model form stars faster from the same amount of raw material. They include altering the assumed initial mass function, the distribution of stellar masses that form when a cloud of gas collapses. They include reducing the feedback effects of supernovae and active galactic nuclei, which in standard models suppress star formation by heating and dispersing gas. Each of these adjustments offers some ability to move the model's predictions in the right direction. The problem is that each adjustment breaks something else. Increasing star formation efficiency in the early universe beyond certain limits conflicts with the statistics of galaxy populations at intermediate redshifts, the universe at a few billion years old, where our observations are most precise and best constrained. Changing the initial mass function in ways that help the early galaxy problem tends to alter the predicted ratios of elements synthesized in stellar interiors, which conflicts with observations of stellar chemistry. Reducing supernova feedback helps early galaxies grow quickly, but creates overproduction of compact, massive galaxies at later epochs that are not observed. Every adjustment that helps the early universe problem creates a problem somewhere else. This is a characteristic sign of a structural tension in a model, not a data problem that more observations will resolve, but a framework problem in which the model's internal relationships resist adjustment in any single direction. The connection to dark matter runs deeper still. Lambda CDM's cold dark matter is cold in a specific sense. It moves slowly, well below the speed of light, and forms gravitational scaffolding on which gas collapses to build galaxies. The rate at which this scaffolding forms and the properties of the earliest structures it supports are determined by cold dark matter's behavior in the early universe. If early galaxies are genuinely more massive than Lambda CDM allows, one possibility is that the dark matter scaffolding formed faster than the cold dark matter model predicts. And if that is true, the problem is not in the galaxy formation physics that sits on top of the framework, it is in the framework itself. Michael Boylan Colchin at the University of Texas at Austin, who has worked on galaxy formation simulations for years, has described the tension between JWEST's early galaxy candidates and Lambda CDM as potentially requiring what he called a substantial change in our understanding of either cosmology or galaxy formation, or both. This is not the language of a researcher who has found a puzzle that a parameter tweak will resolve. Consider what it means to build galaxy formation simulations. Projects like Illustris TNG and Eagle, two of the most sophisticated galaxy formation simulations ever run, require supercomputers operating for months to produce simulated universes that can be compared with observations. These simulations encode the best available models of dark matter clustering, gas dynamics, star formation, supernova feedback, and black hole growth. They represent years of work by large international teams. And what JWEST returned in its first year of observations was a population of objects that these simulations, as currently constructed, do not produce. Every fix proposed for the early universe breaks something in the one we live in now. There is a deeper dimension to the dark matter connection that the JWEST early galaxy problem exposes. The cold dark matter scenario, the CDM in Lambda CDM, predicts a specific hierarchy of structure formation. The first structures to form after the Big Bang should be small. Smaller structures form first, then merge into progressively larger ones. This is called bottom-up or hierarchical structure formation, and it is one of the foundational predictions of cold dark matter. Galaxies form from smaller building blocks that merge over cosmic time. Galaxy clusters form from the merger of galaxies. The largest structures form last. The JWEST early galaxy candidates, if their masses are correct, require top-down elements in the early universe, large structures appearing before smaller ones have had time to merge into them. This is not a small adjustment to the bottom-up picture. It is a reversal of one of cold dark matter's most basic predictions for early cosmic history. And because cold dark matter's hierarchical structure formation is not merely a prediction about galaxies, it is woven into the model's predictions about the large-scale structure of the universe, the distribution of galaxy clusters, the properties of the cosmic microwave background itself. Adjusting it to accommodate the JWEST results is not a local fix. It propagates through the entire model. The second anomaly does not come from JWEST. It does not come from an optical or infrared telescope at all. It comes from two entirely independent methods of measuring the most basic property of our universe, the rate at which it is expanding. The two methods use different instruments, different physical processes, different mathematical frameworks, and different epochs of cosmic history. They should agree. They do not. The rate of cosmic expansion is described by a number called the Hubble constant, denoted h, the speed at which 2 points in the universe move apart from each other per unit of distance. It is measured in kilometers per second per megaparsec, where 1 megaparsec is approximately 3.26 million light-years. The Hubble constant is one of the most fundamental numbers in cosmology. It determines the age of the universe, the scale of cosmic structures, and the ultimate fate of everything we can observe. The first method of measuring h works from the beginning of the universe forward. It uses the cosmic microwave background, the oldest light we can observe, released 380,000 years after the Big Bang, when the universe first became transparent. The CMB's temperature fluctuations encode precise information about the early universe's density, composition, and geometry. Feed those conditions into the standard model, run the equations forward 8 billion years, and the model predicts what h should be today. The Planck satellite, which produced the most precise CMB map ever made, gives a value of 67.4 kilometers per second per megaparsec. The second method works from the nearby universe backward. It uses a chain of distance measurements called the cosmic distance ladder, a series of overlapping techniques, each calibrated against the next, that allow astronomers to measure distances across increasingly large scales. The foundation of the ladder is Cepheid variable stars, whose brightness pulses with a period that is directly related to their intrinsic luminosity. Measure the period, calculate the intrinsic brightness, compare with the observed brightness, and you have the distance. Calibrate Cepheids against objects at known distances, using geometric parallax for nearby stars, and they become reliable distance markers extending hundreds of millions of light-years. Then use those distances to calibrate Type 1a supernovae, which are visible across billions of light-years. Adam Ries and the Suriez collaboration, supernovae H Nero for the equation of state, have been refining this method for decades. Their result, 73.4 kilometers per second per megaparsec. The difference between 67.4 and 73.4 may appear small. In a measurement of an abstract cosmological constant, a gap of 6 kilometers per second per megaparsec might seem like a rounding concern. It is not. Extrapolated across the observable universe's 13.8 billion year history, this difference changes the computed age of the universe, the predicted clustering of matter, and the inferred energy content of dark energy in ways that are physically significant. And the difference has reached 5 sigma. 5 sigma means the probability that this gap is a statistical fluctuation, that both measurements are correct, and the disagreement is noise, is 1 in 3.5 million. In particle physics, a 5 sigma result is what you need before you are allowed to announce the discovery of a new particle. It is not a threshold set casually. It is the threshold that accounts for the many ways a measurement can accidentally appear significant while being wrong. Above 5 sigma, the conventional interpretation is that the measurement is real. The history of this tension makes it more striking, not less. In 2016, when the disagreement between the CMB-based value and the distance ladder value was first clearly articulated, it stood at approximately 3 sigma, suggestive but not conclusive. 3 sigma anomalies appear and disappear in science. They are the kind of thing that gets noted, monitored, and often resolved when more data arrives or when a systematic error is found. The scientific community's expectation was that more precise measurements would bring the two values into agreement. They did not. By 2019, the tension had grown to 4.4 sigma. By 2022 and 2023, with additional distance ladder measurements, gravitational lensing observations from the H-Rho-Lacau collaboration, and surface brightness fluctuation methods added as independent rungs, the tension had reached 5 sigma and was, by some analyses, pushing higher. When a measurement gets worse as data quality improves, it is not behaving like a systematic error. Systematic errors shrink or disappear when instruments are better calibrated and datasets are larger. The Hubble tension has done the opposite. Adam Rees, whose work helped create the distance ladder in its modern form and who has spent decades refining it, has described this as one of the most uncomfortable positions he has occupied in his career, holding 2 measurements he believes are both correctly executed, that are both internally consistent, that agree with all their own internal checks, and that disagree with each other by an amount that should not be possible. 2 teams, 2 methods, 2 answers, and neither one is wrong. In 2018, a small radio telescope in the Western Australian desert picked up a signal from the beginning of time. Not metaphorically. The signal was real radio waves arriving at the telescope's antenna that had been travelling through space for approximately 13.6 billion years. They originated from a period called cosmic dawn, the era roughly 200 to 400 million years after the Big Bang, when the first stars ignited in a universe that had, until that moment, been completely dark. Understanding cosmic dawn is one of the central goals of modern cosmology, because the process by which the first stars formed and ionized the surrounding hydrogen gas set the conditions for everything that came after. Neutral hydrogen, hydrogen atoms in which the electron has not been stripped away, emits radio waves at a very specific wavelength, 21 centimeters. This is the 21 centimeter line, one of the most useful tools in radio astronomy. At cosmic dawn, the universe was filled with neutral hydrogen, and the first star's ultraviolet radiation was beginning to interact with that hydrogen, causing it to absorb the background radiation of the cosmic microwave background at the 21 centimeter wavelength. Detecting this absorption signal from the early universe would give astronomers a direct window into the conditions of the epoch when the first stars turned on. The EDGES experiment, the experiment to detect the global epoch of reionization signature, was built for exactly this purpose. It is a relatively simple instrument by the standards of modern astronomy, a pair of dipole antennas spread across the desert floor, designed to detect the global sky average radio signal at the relevant frequencies. What it found, published in Nature in 2018 by Judd Bowman and collaborators, was the first reported detection of the 21 centimeter absorption signal from cosmic dawn. This was, by any measure, a landmark result, reaching back 13.6 billion years and detecting the faint imprint of the universe's first morning. But the signal was wrong. Not absent, not misidentified, present, confirmed, and wrong in a specific and significant way. The signal was twice as deep as lambda CDM predicts. The model says the absorption should be detectable at a certain level, corresponding to the temperature difference between the neutral hydrogen gas at cosmic dawn and the cosmic microwave background radiation it was absorbing. What EDGES measured was an absorption feature twice as deep as this prediction allows, suggesting that the hydrogen gas at cosmic dawn was significantly colder than the model says it should have been. There are 2 classes of explanation for why the hydrogen might be colder. The first is that dark matter was interacting with the ordinary hydrogen gas at cosmic dawn, transferring energy from the hydrogen into the dark matter and cooling the gas below its expected temperature. This would require dark matter to interact with ordinary matter in a way that the standard model of particle physics says it does not. Dark matter, in our current understanding, interacts with ordinary matter only through gravity. A scattering interaction that would cool hydrogen at cosmic dawn requires a different kind of dark matter. one with properties our current models do not include. The second class of explanation is that there was an additional background of radio radiation at cosmic dawn that no model currently predicts. A radio background intense enough to make the hydrogen's absorption appear deeper relative to the background it was absorbing against. This would require either an unknown population of radio-loud sources in the very early universe, or some other physics that generates a radio background that we do not currently account for. Both explanations require new physics. Neither is contained within lambda CDM as it currently stands. The EDGE's result has not sailed through the community without challenge. Subsequent analyses of the instrument's calibration have raised questions about whether some of the signal's characteristics might reflect foreground contamination rather than genuine cosmological signal. A 2022 analysis using different data found a signal consistent with the EDGE's detection, supporting its reality. Other analyses have been more skeptical. This is the honest picture, an anomalous result in a sensitive measurement, with calibration questions not fully resolved, that has survived enough independent scrutiny to remain an open question in the field rather than being dismissed. It sits in the space of Category 2 claims, real enough to demand continued investigation, contested enough that certainty is not warranted. What is not contested is what the EDGE's signal, if real, would require: physics beyond what we currently have. The coldest signal in the universe came from a time we thought we understood. On the night of May 27, 2021, the Telescope Array experiment in Utah detected a cosmic ray particle striking Earth's upper atmosphere. The Telescope Array is a cosmic ray observatory spread across roughly 700 square kilometers of high desert in Millard County, Utah. 507 surface detector stations laid out in a grid, each one a scintillator that responds when secondary particles from a cosmic ray air shower pass through it. The array was built to detect and characterize ultra-high energy cosmic rays, charged particles, mostly protons and atomic nuclei, that arrive from deep space with energies far beyond anything producible by particle accelerators on Earth. Cosmic rays are not unusual. They arrive continuously, from all directions, across a wide range of energies. At lower energies, they originate from our own galaxy, from supernovae, from pulsars, from the environments around black holes. At very high energies, their sources must be extragalactic. Nothing within our galaxy produces enough power to accelerate particles to the most extreme energies observed. There is a physical limit on how far ultra-high energy cosmic rays can travel. It is called the Zeka limit, after Greisen, Zatsepin and Kuzmin, who derived it independently in 1966. A proton with energy above approximately 510 electron volts, 50 exa electron volts, interacts with photons from the cosmic microwave background as it travels through the universe. The interaction is a pion photoproduction reaction. The high-energy proton collides with a low-energy CMB photon, producing a pion, and the proton loses energy. At energies above the Zeka limit, this process happens rapidly enough that the proton cannot travel more than roughly 160 million light-years without being degraded below the threshold. The universe itself becomes opaque to particles above this energy. An ultra-high energy cosmic ray above the Zeka limit must have originated relatively nearby, within a few 100 million light-years, and from a source powerful enough to accelerate it to those energies. The particle detected on May 27, 2021, had an energy of 244 exa electron volts. That is 2.44 10 electron volts, approximately 5 times above the GK limit. It is the highest energy cosmic ray detected in 3 decades since the famous Oh My God particle was detected by the Fly's Eye detector in Utah in 1991, which reached approximately 310 electron volts and similarly defied easy explanation. The research team, led by Toshihiro Fuji at Osaka Metropolitan University, published their analysis in Science in November 2023. They named it the Amaterasu particle, after the Japanese sun goddess. At 244 exaelectron volts, the Amaterasu particle's GK limit means it cannot have travelled from far away. Tracing its arrival direction backward, accounting for the deflections that magnetic fields in the intergalactic medium would impose on a proton, the team calculated where in the sky it came from. The direction pointed toward the local void, an enormous region of space, centered roughly 150 million light-years from us, that is largely empty of galaxies. Not relatively empty. As far as surveys of the large-scale structure can determine genuinely sparse, a void in the cosmic web of filaments and clusters that constitutes the universe's large-scale architecture. To put the particle's energy in human terms, a single subatomic particle, smaller than a proton, carrying the kinetic energy equivalent of a Major League Baseball pitched at approximately 95 miles per hour. A professional pitch. In a particle with no measurable mass, arriving from 150 million light-years away, from a region of space that contains no known astrophysical source capable of generating it. The known sources of ultra-high energy cosmic rays above the GZK limit include active galactic nuclei, supermassive black holes at the centers of galaxies, actively consuming matter and driving powerful jets. They include magnetars, neutron stars with magnetic fields 1 trillion times stronger than Earth's, capable of accelerating particles to extreme energies. They include gamma-ray burst environments. The arrival direction of the Amaterasu particle, traced backward through the magnetic fields of the local universe, does not point toward any of these, it points toward a void. The Oh My God particle of 1991 also came from an unlikely direction. It also had no identified source. It also remains unexplained more than 3 decades later. The most energetic particle we have ever caught came from empty space. The directional problem is worth dwelling on because it is the specific detail that makes the Amaterasu particle anomalous rather than merely energetic. Ultra-high energy cosmic rays above the Zk limit are expected to point back toward their sources with reasonable accuracy. At those energies, the deflection by intergalactic magnetic fields is limited enough that the arrival direction traces back within a few degrees of the origin. This is what makes them useful. If you can detect enough of them and trace their trajectories, you can build a map of the universe's most extreme particle accelerators. The arrival direction of the Amaterasu particle was determined with an angular uncertainty of a few degrees. Within that error circle, in the region of sky that produced this particle, the large-scale structure surveys find the local void. The local void is not an absence of data. It is a measured, characterized feature of the nearby universe, a region of lower-than-average galaxy density extending for hundreds of millions of light-years in the direction of the constellation Boats. The voidness of the local void is confirmed by multiple independent surveys of galaxy positions and redshifts. It does not contain the kind of objects, active galactic nuclei with powerful jets, magnetar-rich star-forming regions, environments where strong shocks can accelerate particles to extreme energies that ultra-high energy cosmic ray physics says are needed to produce a particle at 244 exaelectron volts. The Oh My God particle of 1991 was eventually catalogued and largely set aside as a single anomalous detection that could not be followed up. The instrument that detected it was not sensitive enough or broad enough to build a statistical sample. The telescope array was built partly to determine whether particles in this energy range are a genuine population with identifiable sources or isolated oddities. The Amaterasu particle is the highest energy event that instrument has recorded. Its source remains unidentified. At this point, the obvious question is whether all of this resolves with better data. It is a fair question. Science has a genuine history of anomalies that turned out to be measurement artifacts. The Opera experiment at CERN reported in 2011 that neutrinos were travelling faster than light, a result that would, if true, have required dismantling special relativity. The result turned out to have two mundane causes: a loose optical fibre connector and an oscillator running at the wrong frequency. Fixed those, remeasured, the neutrinos travelled at exactly light speed. Crisis averted. The 1989 cold fusion announcement, Fleischmann and Pons claiming fusion reactions at room temperature in a tabletop apparatus, could not be replicated by independent laboratories and was eventually attributed to measurement errors and contamination. Science's self-correcting mechanism works. The question is whether what we are dealing with now falls into the same category. And there are specific concrete reasons why each anomaly we have examined resists that explanation. The GIST early galaxy problem is not photometric calibration error. That was the first candidate explanation. Photometric redshifts have known uncertainties, and it was plausible that some of the early galaxy candidates would turn out to be at lower redshifts than initially estimated. Spectroscopic follow-up, which measures specific atomic spectral lines and gives unambiguous distances, was expected to bring the anomalous galaxies back into the model's range. For the best confirmed candidates, it did not. The spectroscopic redshifts matched the photometric redshifts. The masses are real at the distances claimed. The Hubble tension is not a systematic error in either measurement method, and the reason this can be stated with some confidence is that there are now 4 independent methods giving values in the higher range and 1 method giving the lower range, and each method uses different physics. The H-Neuralacau collaboration used strong gravitational lensing, the way massive objects bend light from distant background objects, to measure distances and infer H independently of both Cepheid variables and the CMB. Their result sits closer to the distance ladder's higher value. Surface brightness fluctuation measurements of elliptical galaxies, a 4th independent technique, give a similar result. 4 different physical phenomena, 4 different instruments, 4 different teams, all returning a value inconsistent with what the CMB predicts. A systematic error that simultaneously corrupts 4 independent methods using 4 different physical processes would itself be one of the most extraordinary discoveries in measurement science. The most telling evidence against the systematic error explanation is the trajectory of the Hubble tension over time. In 2016, it was 3 sigma. If it were caused by a systematic error in the early measurements, subsequent improvements should have identified and corrected that error, and the tension should have shrunk. Instead it grew, 3 sigma in 2016, 4 sigma by 2019, 5 sigma by 2022 and 2023. With better instruments, with more precise calibrations, with larger datasets, the disagreement has become more significant, not less. This is not what happens when you are chasing a mistake. It is what happens when you are chasing something real. You might respond, perhaps all 4 distance ladder methods share some subtle systematic bias that has not been found yet. This is possible. But the probability that 4 independent methods developed over decades by separate teams share the same undetected bias pointing in the same direction is, by definition, what the 5 sigma threshold already accounts for. 5 sigma does not mean probably real. It means that the probability of a statistical fluke producing this result by chance is 1 in 3.5 million, even accounting for reasonable estimates of systematic uncertainty. If you believe the answer is still systematic error, you need to explain why that systematic error has survived every test designed to find it. The EDGES signal has calibration questions that remain genuinely unresolved. This is the one anomaly in our set where better data is still being gathered, is the honest answer, and where the verdict is not yet in. But EDGES is not the only data point. It is one of 5, and that is the deeper problem with the systematic error explanation. 5 anomalies across 5 independent fields are not 5 instances of calibration error. The DRESS team's instrument is not connected to the telescope array in Utah. The EDGES radio antennas in Western Australia have nothing to do with the Planck satellite's CMB map. The H-Neuralikaau-Bu gravitational lensing collaboration uses physics that has no relationship to cosmic ray detection. For all 5 anomalies to be systematic errors, each field would have to have made its own independent mistake. And all 5 mistakes would have to point in the same direction toward the same model being wrong in complementary ways. The probability of this is not 0, but it is the kind of probability that in science earns its own name. Better instruments have been tried. They made the problem larger. The oldest image in the universe is a picture of light from 380,000 years after the Big Bang. When the universe was born, it was filled with a plasma so hot and dense that photons, particles of light, could not travel freely. They were constantly absorbed and re-emitted by the charged particles around them. The universe was opaque. Then, approximately 380,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms. In a brief cosmic moment, the universe became transparent. The photons that had been trapped in the plasma were suddenly free to travel in straight lines. They have been travelling ever since. Today, 13 to 8 billion years later, we detect them as the cosmic microwave background, microwave radiation filling the entire sky at a temperature of 725 Kelvin above absolute zero, carrying the imprint of the conditions that existed when they were released. The CMB is the oldest light we can observe. Everything before it is hidden behind the wall of opacity that existed when the universe was younger than 380,000 years. The CMB is the first photograph ever taken of the universe. A baby photograph, encoding in its temperature fluctuations the initial conditions from which everything that followed emerged. Under lambda CDM, the CMB should have a specific set of statistical properties. Its temperature fluctuations should be statistically isotropic, meaning that on average the universe should look the same in all directions. The fluctuations should be distributed according to a specific mathematical pattern across different angular scales determined by the acoustic oscillations of the early universe's plasma. Lambda CDM predicts the shape of this pattern, what physicists call the power spectrum, with extraordinary precision. And when the MAP satellite in the early 2000s, and then Planck with higher resolution from 2009 to 2018, mapped the CMB across the full sky, the power spectrum matched the prediction to a level of precision that confirmed lambda CDM's parameters to within percent-level uncertainties. But in the same high-precision maps, features appeared that the model did not predict. The first is what has become known as the cold spot. Located in the southern constellation Eridanus, it is a region of the CMB sky approximately 1.8 billion light-years across that is statistically colder than the surrounding CMB by a margin that under lambda CDM's predictions for random temperature fluctuations should be extraordinarily rare. It was first identified in map data, and subsequent analysis using Planck's higher resolution confirmed it. Some researchers have proposed that it might be caused by a supervoid, a region of the universe below average density along the line of sight, which would gravitationally cool photons passing through it, but no supervoid of sufficient size and depth has been identified that fully accounts for the anomaly. The second feature is something cosmologists themselves named the axis of evil, not a term coined by science journalists, but by the researchers analysing the data. The name describes a collection of related anomalies. The largest scale temperature patterns in the CMB, called the quadrupole and octupole moments, are aligned with each other and with the plane of the Earth's orbit around the Sun. Under lambda CDM, these large-scale patterns should be random, pointing in random directions on the sky, with no special alignment to any direction in the solar system or the local universe. They are not random, they are aligned. The probability of this alignment occurring by chance under the assumption that the universe is isotropic is small enough to have earned a name suggesting something has gone wrong. The third feature is hemispherical asymmetry. One half of the CMB sky is measurably different from the other in its average temperature power. A universe born from isotropic initial conditions should not have a preferred direction at the largest scales. The hemispheric power asymmetry persists in both WMAP and Planck data. These anomalies exist in the oldest data we have. They have survived the improvement from double map to Planck, a significant increase in resolution and sensitivity that resolved many smaller features while leaving the large-scale anomalies intact. They are not artifacts of low-resolution maps being misinterpreted. They are features of the highest precision map of the CMB ever made. No explanation within lambda CDM fully accounts for all three. Some researchers argue that they could be statistical coincidences, that in a universe where we only have one CMB to look at, seeing something that appears unlikely is not itself evidence that the model is wrong. Others argue that three separate large-scale anomalies in the oldest light we can observe, all confirmed by the most precise instrument ever built, represent a pattern that the model should be able to predict and currently cannot. The universe, at its very first moment that we can see, was already keeping something from us. In 2007, an astronomer named Duncan Lorimer was reviewing archived radio telescope data from the Parkes Observatory in Australia when he found a flash that had no explanation. The signal had lasted approximately 5 milliseconds, 5/1000ths of a second. It was a burst of radio energy arriving from a direction outside the Milky Way, with a characteristic called dispersion, the way lower frequency radio waves arrive slightly later than higher frequency ones after travelling through the diffuse plasma of intergalactic space, indicating that it had travelled an enormous distance. The dispersion measure of the signal implied a source billions of light-years away. From that distance, in 5 milliseconds, the source had released more radio energy than the Sun emits across all wavelengths in roughly 3 days. Lorimer and his colleagues published the detection in 2007. The astronomical community initially received it with uncertainty, a single detection from archival data, of a phenomenon with no identified source and no theoretical prediction was difficult to evaluate. But over the following decade, as radio telescope surveys improved and as astronomers began looking specifically for similar signals, more bursts appeared. Then hundreds appeared. Then the Canadian Hydrogen Intensity Mapping Experiment, CHIME, a radio telescope in British Columbia designed primarily to map dark energy through the distribution of hydrogen in the universe, began detecting fast radio bursts at a rate that transformed the field. In its first year of operation, CHIME detected more FRBs than had been found in all previous years combined. The rate of fast radio bursts across the observable universe, based on CHIME's detection statistics, is estimated at somewhere in the range of thousands per day. The universe is producing these millisecond flashes of extraordinary radio energy constantly, from billions of light years away, in every direction. A partial explanation came in April 2020, when the CHIME telescope and other observatories detected a fast radio burst from within our own galaxy, FARB 22428, traced to a magnetar called SGR 1935+2154. Magnetars are neutron stars with magnetic fields reaching 10 Gauss, a trillion times stronger than Earth's magnetic field. The violent rearrangement of a magnetar's magnetic field can release enormous amounts of energy in very short timescales. The detection of a galactic FRB from a known magnetar was the first direct evidence linking fast radio bursts to a specific type of astrophysical source. It was a genuine milestone. But the milestone resolved one question while leaving others open. The repeating fast radio bursts, sources that produce multiple bursts, sometimes in patterns, present characteristics that magnetar models struggle to account for. FRB 22001-24A, one of the most extensively studied repeating sources, shows sub-burst frequency drifts, varying polarization behaviors, and burst-to-burst morphology changes that magnetar emission models predict poorly. FARB 2220912A showed quasi-periodic activity windows, periods of activity separated by periods of silence, in a pattern that, while not perfectly regular, occurs at a rate that random magnetar activity cannot easily explain. The detailed phenomenology of repeating FRBs contains features that remain without a satisfactory model. Beyond the source physics, fast radio bursts have become precision instruments. Because each FRB's dispersion measure accumulates from the plasma it travels through, FRBs from precisely localized host galaxies can be used to measure the distribution of ordinary matter between galaxies, the baryon density of the intergalactic medium. These measurements have begun to show mild tensions with what lambda CDM predicts for the intergalactic baryon distribution, adding a sixth dimension of measurement to the picture. CHIME was built to map dark energy. It became the world's most productive FRB detector. The instrument that was asked to probe the universe's structure is now returning, as a byproduct, the most energetic millisecond events ever catalogued. And some of those events are not fully explained by anything we currently have. We have named them. We have counted them. We have not explained them. The energy argument for fast radio bursts deserves fuller development, because it is one of the places where the gap between observation and theory is most stark. A millisecond is 1,000th of a second. In that interval, a fast radio burst releases radio energy equivalent to what our sun emits across all wavelengths, not just radio, but the entire electromagnetic spectrum from gamma rays through radio over a period of roughly 3 days. The source of this energy, whatever it is, must be compact enough to vary on millisecond timescales, which sets an upper limit on its physical size through the light-crossing argument. Nothing larger than the distance light travels in 1 millisecond, about 300 kilometers, can coherently produce a millisecond duration pulse. The energy reservoir must be packed into an object no larger than a major city. Magnetars satisfy this size constraint. Neutron stars are city-sized objects with enormous energy reservoirs in their magnetic fields. But the magnetar in our own galaxy that produced FRB 2400428 released a burst that, while comparable to extragalactic FRBs in its physical nature, was orders of magnitude less energetic than the cosmological FRBs detected at billion light-year distances. Scaling up the galactic magnetar burst to match the energy of the most luminous extragalactic FRBs requires either that the cosmological sources are fundamentally different from the galactic magnetar, or that magnetars have an energy output range spanning orders of magnitude that current models do not predict. Either possibility opens questions that the field has not resolved. The cosmological utility of FRBs, using their dispersion measures to probe the intergalactic medium, adds a further layer of relevance. Because every photon in an Ferb pulse travels through all the plasma between its source and Earth, and because lower frequencies travel slightly slower through plasma than higher frequencies, the arrival time difference between frequencies encodes the total electron column density along the line of sight. This is the dispersion measure. Comparing dispersion measures of FRBs at known distances against what lambda CDM predicts for the baryon density of the intergalactic medium is a precision cosmological test. The results from the growing Ferb catalogue show mild but real tensions with the model's predictions for where ordinary matter is distributed between galaxies, another line of evidence from another independent technique, that the model's description of the universe is under pressure. There is a distinction between one anomaly in one field and 5 anomalies in 5 fields that all point in the same direction. A single anomaly, even a significant one, could be an instrument artifact, an unidentified systematic error, a measurement technique with a flaw no one has yet identified. The history of science contains examples of apparently significant anomalies that resolved with better data or sharper analysis. No single anomaly by itself demands that a successful model be revised at a fundamental level. This is why scientists are cautious. This is why 5 sigma exists as a threshold rather than 3. Caution is the appropriate response to a single measurement that contradicts expectation. But the situation in cosmology right now is not a single anomaly. Consider what is on the table. The Dwest-Early galaxy problem comes from optical and infrared astronomy, the study of light in the wavelengths where stars and galaxies emit most of their energy. It uses redshift measurements of distant galaxies and stellar population synthesis models. The Hubble tension comes from cosmological distance measurement, a completely different enterprise using Cepheid variable stars, Type 1 supernovae, and strong gravitational lensing to build a distance ladder across the observable universe. The Edge's 21 cm signal comes from radio astronomy in the specific frequency range corresponding to the redshifted 21 cm hydrogen line from the early universe. The Amaterasu cosmic ray comes from cosmic ray physics, the study of charged particles arriving from space, detected through the particle showers they produce when they strike Earth's atmosphere. The CMB anomalies come from microwave astronomy, mapping the temperature of the oldest light in the universe across the full sky with satellite instruments. 5 different phenomena. 5 different physical processes. 5 different detection techniques. 5 different teams of researchers working in 5 different subfields of astronomy and physics, using 5 different types of instruments, asking 5 different questions about the universe. If anomalies were random noise, errors distributed randomly through the measurement process, they would point in random directions. Some measurements would come in slightly above the model's predictions, others slightly below. The deviations would not be systematically correlated, and crucially, anomalies in one field would not be complementary to anomalies in another. They would simply be scattered noise. What we observe is different. The Dwest-Early galaxy problem suggests the universe formed structure faster in the early universe than lambda CDM predicts. The Hubble tension suggests the expansion rate of the late universe is faster than the CMB-based extrapolation of the model predicts. The Edge's signal, if real, suggests the conditions at cosmic dawn were different from what the model describes. The Amaterasu particle suggests there are either unknown sources or unknown propagation effects in the universe at the highest energies. The CMB anomalies suggest large-scale anisotropies in the universe's structure that the model does not predict. These are not 5 random deviations. They are 5 deviations that are broadly consistent with a picture in which the universe has been forming and organizing structure more efficiently than lambda CDM allows, in which the early universe was more active, more structured, more energetically complex than the model's smooth initial conditions produce. There is a 6th measurement worth naming here. It is called the S8 tension, a disagreement between 2 measurements of how clumped matter is in the universe on intermediate scales. The parameter S8 combines the overall matter density with the amplitude of matter clustering. The Planck CMB analysis predicts a specific value of S8 based on the model. Weak gravitational lensing surveys, which measure the distortion of distant galaxy shapes by the gravitational effects of matter along the line of sight, have found values approximately 2 to 3 sigma lower than Planck predicts. The KIDS 1000 survey and the Dark Energy survey have both found this result independently. This is a 6th independent measurement, a 6th field, a 6th team, a 6th technique. It points in the same direction as the others. Wendy Friedman, whose work with the tip of the red giant branch method was initially hoped to clarify the Hubble tension by providing an independent distance ladder measurement, found that her TREG-B results sat between the 2 competing values but resolved neither. Rather than splitting the difference and providing a path toward reconciliation, the TREG-B measurement added complexity to the picture, a 3rd independent result that was difficult to cleanly reconcile with either the high value or the low value of the Hubble constant. Research communities in cosmology have responded formally. The Hubble tension has been the subject of dedicated conferences and workshop series. It has been reviewed in the Annual Review of Astronomy and Astrophysics, the field's premier review publication, by leading researchers who have assessed the evidence and concluded that systematic errors in any single measurement cannot account for the discrepancy. This is not fringe discussion happening outside peer review. It is the central concern of the field's most prominent practitioners, conducted in the highest prestige venues available to the discipline. 5 fields, 5 anomalies, 1 model under pressure from all 5 simultaneously. The convergence argument has a formal dimension that is worth stating explicitly. When scientists evaluate a set of measurements, they ask not just whether each measurement is consistent with the model, but whether the pattern of deviations is random or systematic. A model that is correct should produce deviations that scatter randomly around its predictions, some measurements slightly high, some slightly low, distributed without pattern. A model that is systematically wrong in a particular way should produce deviations that cluster on one side, or that correlate with each other across different types of measurement. The current anomalies are not a random scatter. They are correlated. The Dressed Early Galaxy problem and the Hubble tension both suggest the universe has been more active and has formed structure more efficiently than lambda CDM predicts. The S8 tension suggests matter in the present universe is less clumped than the CMB-based prediction expects, which could reflect either that the early universe imprinted less structure than the model computes, or that the growth of structure since then has been suppressed relative to predictions. The Edges anomaly, if real, suggests the early universe's energy budget and the behavior of dark matter at cosmic dawn were different from the model's description. These are not deviations in random directions. They form a pattern, an incomplete pattern with too few data points to specify exactly what model would replace lambda CDM, but a pattern nonetheless. The researchers working in the field are aware of this. The formal language is coherent anomalies, deviations that when viewed together suggest a common underlying cause rather than independent statistical fluctuations in independent measurements. Identifying coherent anomalies is the first step in the process that eventually produces new physics. It is the step that precedes the development of alternative models, the design of experiments to test them, and the eventual confirmation of whatever the correct extension turns out to be. Cosmology, by the assessment of researchers inside it, is currently in the coherent anomaly stage of this process. The question that follows from all of this is the hardest one in the field. It is not whether any individual anomaly is real. The Hubble tension is real enough that its discoverers include a Nobel laureate who has spent years confirming it. It is not whether the anomalies will eventually be resolved. Science resolves things eventually, almost by definition. The hard question is what kind of resolution is possible, and the honest answer is that the options range from the relatively straightforward to the genuinely unprecedented. The relatively straightforward option is parameter adjustment. Lambda CDM has parameters, numbers that describe things like the density of dark energy, the behavior of dark matter, the equation of state governing the relationship between pressure and density in the early universe. If one or more of these parameters is slightly wrong, then refining the model's parameters rather than its structure might resolve some or all of the anomalies. This is the best-case scenario. Better measurements, more precise data, and the tensions narrow to something the model can accommodate. The problem is that this option has been tried. Early dark energy models, which add a component of dark energy active in the very early universe that then fades, boosting the expansion rate in the early universe and thereby affecting the Hubble constant, can reduce the Hubble tension by some amount. But they do so at the cost of worsening the S8 tension and creating new disagreements with large-scale structure statistics. Interacting dark matter models, in which dark matter and ordinary matter interact in ways beyond pure gravity, can help the edges anomaly, but require dark matter properties inconsistent with the constraints from galaxy formation. Modified gravity theories, alternatives to general relativity at cosmological scales, alleviate some anomalies and create others. Every model extension that has been tried is like pressing on a balloon. The tension disappears in the place you press and reappears somewhere else. No single modification resolves all anomalies simultaneously without creating new problems elsewhere. This is the signature of a structural tension, not a parameter problem, but a framework problem. The model's internal relationships are resisting simultaneous adjustment in the directions the anomalies require. This leads to the harder option, not adjusting lambda CDM, but extending it the way general relativity extended Newton. Newton's mechanics was not wrong, it was incomplete. Within its domain, objects moving slowly compared to light, gravitational fields that are not extremely strong, it remains exact to any practical measurement. But Mercury's orbit around the Sun precesses slightly faster than Newtonian gravity predicts, 43 arcseconds per century, a deviation so small that it required extraordinarily precise observations to detect and confirm. The deviation survived 2 centuries of scrutiny. It required a completely new framework, general relativity, to explain. And when general relativity was developed, it did not merely fix Mercury, it simultaneously predicted gravitational time dilation, the bending of light around massive objects, gravitational waves, and the existence of black holes, none of which anyone had specifically asked for. The extension of Newton's framework produced an entirely new picture of what space, time, and gravity are. George F. Stathiou at Cambridge, who co-received the Nobel Prize for his work on the CMB's power spectrum and is one of the architects of modern cosmological analysis, has stated in public talks and papers that the Hubble tension is not going away and may require new physics, a term that, in this context, means a framework extension of the type that general relativity represented relative to Newton. Not the replacement of lambda CDM, but the discovery that lambda CDM is a limiting case of something more general, valid in the domain where we have tested it, but insufficient in domains that our improving instruments are now reaching. The hardest option, and the one that cannot yet be ruled out, is that what we are finding in deep space requires not just a framework extension, but a conceptual expansion for which we do not yet have the mathematics. Some of what we are measuring may be beyond the reach of current concepts in the way that quantum mechanics was beyond the reach of classical mechanics before Planck and Einstein and Bohr and Heisenberg built the tools to describe it. Not wrong physics, not better data applied to existing equations. A new language for describing phenomena that the current language cannot express. This possibility does not mean that our existing knowledge is discarded. Quantum mechanics did not invalidate Maxwell's equations of electromagnetism within their domain. General relativity did not invalidate Newton within the domain where objects move slowly and gravity is weak. Whatever comes after lambda CDM, if something must come, will not invalidate its confirmed predictions. It will extend them into territory where they currently fail. We do not yet have the theory to hold them. This specific situation, anomalies that survive scrutiny, that grow stronger with better data, that appear in independent fields simultaneously, has happened before. It happened in 1905. The photoelectric effect, the ejection of electrons from metal surfaces by light, had been observed since the 1880s, but could not be explained by the wave theory of light that was the accepted framework at the time. The wave theory said that the energy of ejected electrons should depend on the intensity of the light illuminating the metal. Experiments showed it did not. The energy of ejected electrons depended only on the frequency of the light, its colour, not on its brightness. Brighter light ejected more electrons, but at the same energy. This was a clean, reproducible, well-confirmed experimental result that the accepted framework could not explain. In 1905, Albert Einstein published a paper proposing that light comes in discrete packets of energy, called photons, and that the energy of each packet is proportional to the light's frequency. The equation fit the data exactly. This paper, for which Einstein received the Nobel Prize in 1921, was one of the founding documents of quantum mechanics. It did not destroy wave optics. It revealed that light is both a wave and a particle, a more complete picture that contains wave optics as a limiting case. It also happened in the 1850s through 1910s. Mercury's perihelion, the point in its orbit closest to the Sun, precesses, meaning it slowly rotates around the Sun over time. Newtonian gravity predicts a precession rate from the gravitational tugs of other planets. The observed precession is 43 arcseconds per century faster than Newton predicts. This discrepancy was confirmed by increasingly precise observations over 6 decades. No Newtonian explanation worked. Proposals of an inner planet pulling on Mercury or adjustments to the inverse square law all failed. In 1915, Einstein's general theory of relativity, developed for reasons that had nothing specifically to do with Mercury, predicted exactly 43 arcseconds per century of additional precession as a consequence of the curvature of space-time near the Sun. Mercury's anomaly had survived 60 years of scrutiny because it was real. It was the universe showing the edge of Newton's map. But the most directly relevant precedent is 1998. The anomaly then was the discovery that the expansion of the universe is not slowing down, as gravity would predict, but accelerating. 2 teams, the Supernova Cosmology Project and the High Z Supernova Search Team, including Adam Ries, published results from surveys of Type 1a supernovae that showed distant supernovae to be farther away than they should be if the universe's expansion were decelerating. The universe was expanding faster and faster, driven by something that had not been predicted and was not then understood. Lambda CDM was extended to include the cosmological constant lambda, Einstein's originally rejected term, representing the energy density of empty space, which would produce exactly the accelerating expansion observed. Dark energy was added to the model. Lambda CDM as we know it was born from an anomaly that survived scrutiny. The researchers who discovered cosmic acceleration received the Nobel Prize in 2011. The anomaly that they were tracking, the one that seemed to contradict the accepted model of a decelerating universe, turned out to be the key to the most significant revision of cosmology in decades. The current situation involves more anomalies, in more fields, with more independent lines of evidence than any of these historical predecessors. If the current pattern leads to an extension of Lambda CDM, the extended model will need to simultaneously account for early galaxy formation, the Hubble tension, the CMB anomalies, the Edges signal, the Amaterasu particles origin, and the S8 tension. Any framework that does this will almost certainly predict additional phenomena that have not yet been looked for, the way general relativity predicted gravitational waves before there was any instrument capable of detecting them. The instruments being built now will be the ones that determine which direction the resolution goes. The Vera C. Rubin Observatory in Chile has begun its legacy survey of space and time, a 10-year program that will image the entire southern sky every few nights, accumulating data on billions of galaxies and providing the most precise weak gravitational lensing measurements ever made. These measurements will sharpen the S8 tension either toward resolution or toward a clearer demand for new physics. The CMB Stage 4 experiment, a ground-based array targeting the mid-2030s, will measure the CMB temperature and polarization with sensitivity sufficient to detect or constrain a wide range of new physics proposals. The Nancy Grace Roman Space Telescope, currently in development, will provide independent supernovae measurements that will either confirm or challenge the distance ladder's high Hubble constant value. And the LISA mission, the Laser Interferometer Space Antenna, a gravitational wave observatory in space targeted for approximately 2035, will measure the Hubble constant using merging compact binaries as standard sirens, entirely independent of both the CMB and the distance ladder. If LISA returns a value consistent with the distance ladder, the case for new physics becomes overwhelming. If it returns a value consistent with the CMB, the resolution lies in the distance ladder methods. Either outcome is progress. Every time physics found itself here, it did not collapse. It expanded. In observatories and university offices and data centers right now, people are doing something that has no dramatic name for it. They are sitting with data that does not fit. Not metaphorically sitting, looking at numbers on screens, running analysis pipelines, writing code that checks and rechecks calibration, attending conferences where the same tensions are presented from different angles by different teams who have all done the same checks and arrived at the same uncomfortable results. This is what the inside of a scientific anomaly looks like from the people living in it. It is not exciting in the cinematic sense. It is methodical, careful, and in its own quiet way, relentless. Adam Rees has described his position on the Hubble tension as one of the more unusual experiences of his career. He has spent decades building the cosmic distance ladder, calibrating Cepheid variable, refining the supernova measurements that helped discover cosmic acceleration, receiving the Nobel Prize for that work. He knows the distance ladder's systematic uncertainties better than almost anyone alive. He has spent the years since the tension became statistically significant not looking for evidence that the tension is real. It is, but searching for any systematic error in his methods that would make it go away. He has not found one. The discomfort is not in suspecting the result. The discomfort is in having checked and checked and checked and found the result still standing. The dress science team was not expecting the early galaxy results. In interviews following the first-year publications, team members expressed genuine surprise at the size and maturity of the galaxy candidates appearing at the highest redshifts. This was not the experience of finding what they went to look for. It was the experience of pointing the best instrument ever built at the question the field had been asking for decades: what does the early universe look like? And receiving an answer that the field was not prepared for. Toshihiro Fuji and his colleagues at the telescope array spent months after the Amaterasu particle's detection tracing its arrival direction backward through the magnetic fields of the local universe. The calculation is not trivial. Ultra-high-energy cosmic rays are deflected by magnetic fields as they travel, and the intergalactic magnetic field is not well mapped. But at the energies of the Amaterasu particle, the deflection is small enough that the arrival direction can be traced within a few degrees. Within that error circle, the local void. Fuji has described the source as unknown. He did not say the source is mysterious, or exciting, or alarming. He said it is unknown, the precise, neutral language of a researcher holding a result that the current map cannot place. What each of these researchers is doing, in their respective fields, is the same thing. They are at the edge of the map. The map they have is the best map that has ever been built. It was built over decades by thousands of researchers using instruments of extraordinary precision. It correctly describes an enormous amount of what we observe. And it stops, not because anyone decided to stop, but because the territory extends beyond where the map currently reaches. The instruments coming in the next decade will tell us whether the edge of the map is a place where a new map begins, or a place where the existing map can be extended with better measurements. The Rubin Observatory is already accumulating galaxy data, the Roman Space Telescope is in preparation, the CMBS-4 array is being planned, LISA is being built. What each of these instruments will add is not just better data, it is independent data from independent physical processes, adding independent lines of evidence to a picture that currently has too few to determine its own resolution. The work continues because the data has not stopped arriving. There is a quality of patience in this work that deserves naming. The Hubble tension has been the defining anomaly of Adam Riess's career for nearly a decade, since the first time the distance ladder and CMB values came apart at a statistically significant level. For a decade, the expectation in the community was that it would resolve. Each new measurement was supposed to be the one that found the error, or confirmed that the values were converging. Each new measurement instead maintained or widened the gap. Sitting with that result, being the person whose measurement is at 5 sigma odds with the most precisely validated model in the field, knowing that the measurement is correct, not knowing why the disagreement exists, is an experience that has no parallel in ordinary scientific work. The Edges team occupies a different kind of uncomfortable position. Their result is real enough to remain in the literature, significant enough to have generated dozens of follow-up papers, and contested enough that the broader community has not reached a consensus on whether the calibration is fully understood. Working in that space, having detected something that may be one of the most important signals in the history of radio astronomy, and being unable to provide the community with the certainty that would allow a definitive verdict, is a kind of sustained uncertainty that the normal structure of scientific publication does not prepare researchers for. Papers get published. Results either replicate or fail to replicate. The edges result occupies a middle state, significant, contested, The telescope array team knows that their most energetic detection has no identified source. Fuji and his colleagues have published the analysis. The cosmic ray community is aware of the Amaterasu particle. The response has been to look harder, to review the large-scale structure maps of the local void region at greater sensitivity, to analyze the deflection calculations under different assumptions about the intergalactic magnetic field, to look for additional high-energy events from the same direction that might help constrain the source. None of this has resolved the question. The particle arrived. Its source remains unknown. And the telescope array continues to operate, waiting for the next event that might help clarify the picture. The anomalies we have been talking about are not headlines. They were not announced at press conferences with dramatic graphics and simplified summaries. They emerged slowly, in papers with careful language, in measurements that were repeated and rechecked and reported with appropriate uncertainty ranges, in conferences where researchers from competing groups compared results, and found, to their collective discomfort, that they could not make the disagreements go away by any means available to them. What the title of this script calls worry is something more precise than that word usually conveys. It is the specific experience of standing at the edge of a framework and finding that the territory does not match the map, not finding that everything you know is wrong. Lambda CDM correctly predicts the CMB power spectrum. It correctly predicts the abundances of hydrogen and helium synthesized in the Big Bang. It correctly predicts the statistical properties of galaxy clustering at intermediate scales. These predictions stand, confirmed by measurements of extraordinary precision. The model is not wrong. It is, in some domain or domains, incomplete, and the instruments are now sensitive enough to find the places where the incompleteness shows. This is different from ignorance. Ignorance is not knowing that a territory exists. What we are describing is knowing exactly where the map ends, being able to point at specific measurements and say, here, at 5 sigma, the model fails to account for the expansion rate. Here, at the edge of Dresst's reach, the model fails to account for the galaxies we are finding. Here, in the oldest light we can observe, the model fails to account for the large-scale patterns we see. The edges of the map are precisely located. That precision is itself a kind of knowledge. The honest statement of where cosmology stands is this: Lambda CDM is the most successful model in the history of the field. It correctly describes the universe we observe across an enormous range of scales and phenomena. And it is under pressure from multiple independent directions at a statistical significance that demands attention, from anomalies that have survived every systematic check applied to them. We do not currently have a replacement. We have candidates, model extensions that resolve some tensions and create others. We have instruments being built that will sharpen the picture within this decade. We have researchers who are doing the work with the rigor and patience that the problem deserves. What we do not have is the resolution, and the honest acknowledgement of that is not a failure. It is the most accurate description of where we are. There is something specific about living in the era when the instruments are just good enough to find the edges of the map. Every previous era of astronomy had maps that looked complete, until something pushed past their edges. The map of the solar system looked complete until telescopes resolved the structure of Saturn's rings and showed moons no one had seen. The map of the galaxy looked complete until Hubble resolved individual stars in the Andromeda Nebula and showed that it was a separate galaxy entirely. The map of the static universe looked complete until redshift measurements showed that galaxies were receding and the universe was expanding. Each time the edge of the map was not a failure. It was the address of the next map. We are not lost. We are at the edge of the map, which is exactly where the next map begins. There is something specific about this particular edge that is worth sitting with. Previous edges of cosmological maps were found by pushing further in one direction, observing more distant objects, measuring fainter signals, building larger telescopes. The expansion of the universe was found by looking further away than anyone had looked before. The CMB was found by opening the microwave window that radio technology made accessible. In each case, the edge was found in a direction that was obviously unexplored. Further, fainter, higher energy, lower frequency. The current edges are different. They are being found not at the limits of what we can observe, but in the precise measurement of things we have been observing for decades. The Hubble tension is not at the edge of what we can see. It is in the most fundamental measurement in cosmology, applied to the nearest and the most distant objects we can measure, with instruments that represent the pinnacle of current technology. The CMB anomalies are not at the limit of sensitivity, they are in the most precise map of the oldest light ever made. JUICE's early galaxy candidates are at high redshift, yes, but the anomaly is not in the redshift. It is in the masses, calculated from the same stellar population physics that has been applied to galaxies for decades. This means the edges are not going to be resolved simply by building a more powerful telescope pointed in the same direction. They are going to be resolved by finding what the current framework is missing, what concept, what component, what relationship between physical quantities is not yet in the model. That is a more difficult problem than pushing further in a known direction. It is the kind of problem that requires not just more data, but new ideas about how to interpret the data we already have. It is the kind of problem that, historically, has taken decades to resolve, and has produced, when resolved, the most significant advances in the history of physics. We do not yet have a model that accounts for all of it. This is the honest gap statement, offered with. We do not have a resolution to the Hubble tension, a measurement sitting at 5 sigma for which no modification of lambda CDM simultaneously resolves the early universe CMB value and the late universe distance ladder value. We do not have an identified source for the Amaterasu particle, the most energetic cosmic ray detected in 3 decades, arriving from a direction that surveys of the large-scale structure find largely empty. We do not have a confirmed explanation for the edge's 21 cm signal, whether the anomalous depth is caused by dark matter interactions, an unknown early radio background, or an unidentified calibration effect is genuinely unresolved. We do not have a galaxy formation model that produces the JUICE early galaxy candidates within the current lambda CDM framework, the parameter adjustments that help the early universe problem break the late universe predictions. These are specific, precisely stated gaps. They are not vague gestures at the unknown. They are the current frontier of the field, marked with coordinates. What we do have is equally specific. JUICE continues to operate. Every month it returns new observations from the deep universe, adding to the catalogue of early galaxy candidates, and providing the spectroscopic confirmations that determine which of them are genuinely anomalous. CHIME continues to detect fast radio bursts at a rate that was unimaginable a decade ago, building a dataset that will eventually constrain the intergalactic medium's baryon distribution well enough to test cosmological models. The telescope array continues to monitor ultra-high-energy cosmic rays, looking for more events in the Amaterasu class and for the arrival direction correlations that would identify their sources. The Planck data continues to be analysed. Cosmologists are still finding new measurements in the most complete CMB map ever made. The Rubin Observatory has begun its decade-long survey of the southern sky, and its weak lensing measurements will be among the most important data products of the 2020s. The S8 tension that comes from those weak lensing surveys, the discrepancy between the clumpiness of matter that the CMB predicts and the clumpiness that surveys of the actual galaxy distribution find, will be sharpened by Rubin's data to the point where a definitive statement becomes possible. Either the tension will narrow as the survey data grows and the analysis improves, which would suggest a statistical or systematic origin, or it will remain at 2 to 3 sigma with greatly reduced uncertainties, which would make it a clean, independent line of evidence demanding new physics. If what we have discussed tonight stays with you, the Hubble tension, the early galaxies, the particle from the local void, consider sharing this with someone who asks the right questions. The science discussed here is real, the papers are public, and the researchers named are working on it now. This is not a field in crisis, it is a field in contact with something real. The anomalies are data. Data is what science runs on. The appropriate response to data that does not fit a model is not alarm and not dismissal. It is the careful, unglamorous work of determining whether the model is insufficient, and if so, in what direction the new model must extend. This work is being done. It will continue to be done. The instruments coming online in this decade will provide data sufficient to settle several of the current questions, and will likely open new ones. The data keeps arriving, the questions keep sharpening. That is what this looks like from the inside. There is a word cartographers once wrote at the edges of their maps. Beyond the places they had sailed and surveyed and confirmed, beyond the coastlines they had charted and the depths they had measured, the maps gave way to open space. Sometimes the cartographers wrote simply unknown territory. Sometimes they described what was reported to be there: strange currents, unusual winds, accounts from sailors who had returned with stories that didn't fit the maps they carried. The map was not wrong about the territory it described. It was simply the edge of what had been reached. What astronomers are finding in deep space now is what cartographers found at the edges of their maps. Not that the known territory was wrong, not that the laws governing what they had charted had failed, but that the territory extends further than the map, and that at the edge of the map, the universe does not look quite like what the map predicted. The researchers holding these measurements, Adam Ries with his distance ladder and its 5 sigma disagreement, Evo Lab and his collaborators with their early galaxy candidates that formed in a window of time shorter than complex life on Earth, Toshihiro Fuji with his particle from the local void, the CHIME team cataloguing hundreds of fast radio bursts per year, are doing what all cartographers do at the edge of the known, mapping precisely where the map ends, describing exactly what they see there, and building the instruments that will extend the map further. This is not the beginning of the end of understanding. It is the continuation of a process that has no end, of building maps, reaching their edges, and finding that the territory demands a larger map. Every previous version of this moment in the history of physics produced not collapse, but expansion. Newton's mechanics expanded into general relativity. Classical physics expanded into quantum mechanics. A static universe expanded into the Big Bang. An expanding universe expanded into an accelerating one. What comes after lambda CDM, whether it is a parameter refinement or a new framework or something for which we do not yet have a name, will describe more than lambda CDM described. It will account for the galaxies JWST is finding and the expansion rate the distance ladder is measuring and the particle that arrived from the local void. It will be, by definition, a more complete picture of what the universe is. We built the current map from one small planet. We built instruments sensitive enough to find its edges. We are standing at those edges now, looking at territory that the map does not yet cover. The specific anomalies we have examined tonight, the early galaxies, the expansion rate, the cosmic dawn signal, the particle from the void, the oldest light's unexpected features, the millisecond flashes from the distant universe, are the places where the current map gives way to open space. They are not defects in the map, they are its edges, precisely located. And the fact that they can be precisely located, that we can say here, at 5 sigma the model fails, and here, in the direction of the local void, the particle arrived from nothing we can name, is itself a product of the map's extraordinary accuracy in every direction that is not an edge. The researchers will continue, the instruments will continue, the data will keep arriving from deep space, from instruments pointed at the same sky from the same planet, returning numbers that the best model humanity has ever constructed cannot fully account for. This is the specific dignity of the work, not the moments of confirmation, but the sustained, careful attention to the places where the universe refuses to be smaller than the model built to describe it. The map has always had edges. We have always built the next one. If this is where you come to think, subscribe so you find your way back. Good night.